All right, for this topic, what we're going to do is we're going to spend a little bit of time going over the concept of graphing rational functions. Now, in your geometry class next year, Ms. Coop teaches geometry pretty much for 3 quarters actually. And in the last quarter, she teaches some other topics in algebra, like exponential functions, logarithmic functions, power functions. I think that's it, those 3 in the last quarter. And so one of the topics that you usually do cover in pre-calc that is easier for us to cover now, so you don't have to do it in pre-calc because it involves a lot of the stuff we've been talking about, zeros of functions, looking at synthetic division and stuff. We're going to cover now. So these are notes that are not in your text. Okay, there's no questions in your text for this. There's a little part at the end of chapter 5 about graphing rational functions, but I've kind of written my own notes for this, and there's a lot more details. We're going to do a lot more with it than just that. In the last few years, I was kind of rushed at the end of the year to get through this, so I didn't make slides with notes. So I can do that for the next section if you'd like, or you can honestly just follow along. So if you notice, if you're looking at the notes right now and you scroll down a little bit, scroll to the second page, you're going to see the notes are all completed for you already. So you can just follow along, but still write yourself little notes along the way. Draw little things in the diagram, point out different spots in the diagram that are important, but all the notes are kind of here for you right now. Okay? So in this section, we're going to talk about 4 main objectives. First, looking at the general shape of rational functions. Second, looking at the characteristics. We're going to talk about end behavior and what are called asymptotes. And then we're going to talk about discontinuities and holes and what are called vertical asymptotes. The other ones are called horizontal asymptotes. Horizontal, vertical. Some terminology that we really need to know. The word rational, what does it mean again? What does rational mean? If a number is rational, it can be written from like as a fraction. A number that's rational can always be written as a fraction. So if we're looking at rational functions, we're looking at what we call the ratio of 2 polynomials. Well, what's a ratio really? A fraction. A ratio of 2 to 5, 2/5. 3 to 7, 3/7. It's a fraction. So we're looking at one polynomial over another polynomial. So we can see how this is alluding to synthetic division or long division that we've been studying recently, okay, in chapter 8. The second term I want to discuss is called end behavior. So, tell me something, please, okay? Looking at this graph here, what do you think might be an example of something that would behave with that kind of motion? What would something in real life be that would oscillate, but then the oscillations would die off? Well, a sound wave. It's a great example. You pluck a guitar string, right? Doesn't it oscillate for a while? Then what happens? Oscillations diminish. You hit a piano key. It's the string oscillates, vibrates, and then it dies off. You drive in your car. You hit a little speed bump. What happens? The hydraulics of the car, what do? And then the car flies off. And you continue to ride slowly. But that's physically what happens, right? So, what could you tell me about this function? As time progresses, the function tends to go toward where? The x-axis, which as a y value, what y value is that? What y value is the x-axis always? Think about any coordinate. What is it? 0. Y equals 2 is this line. Right? I'll point on the graph so you can see this. So here's y equals 2, right? Look, it's this line right here. Y equals 3 is right here. Y equals -5 is down here. Well, this graph is slowly getting closer and closer to 0. So I could write this. As x gets larger, y tends to go toward 0, doesn't it? I could write that relationship. That's what end behavior is. That's the easiest way to explain end behavior without giving a statement. An example is so much easier. So end behavior is what happens to the function as x progresses toward infinity. Or, as x progresses toward, what's the opposite of infinity? Negative infinity. Now, in this graph, we can't tell what happens as it approaches negative infinity because we don't know anything more about this. Maybe it turns back around. We don't know enough. But as it goes toward infinity, it's clear that this graph is going toward y equals 0. What about something like this? Tell me what the end behavior would be for a graph that looks like this. How about this one? The blue graph. The blue graph. What would you say its end behavior is? As x goes to infinity, what is it going toward? What is it getting closer and closer to? Negative 3. Do you see the horizontal dashed line at negative 3? Negative 1, negative 2, negative 3, right? There's a horizontal dashed line there. That means that the end behavior is as x goes to infinity, y goes toward negative 3. Okay? These are end behaviors that are going towards something. Sometimes they don't go toward anything. Well, what about this? A straight linear function. Or not straight, a linear function that constantly increases. Well, as I get further and further this way, where does the graph go, guys? It goes up. I go further, where does it go again? Up. So as x gets bigger, what also happens to y? It gets bigger. So the end behavior for this would say, as x gets bigger, y, what? So what would I write? As x goes to infinity, y goes to infinity for this graph. Okay, so we'll talk about end behavior in this section mathematically, how we can use it, but I want you to see visually what it goes like. Okay, the same thing occurs in this graph in the opposite direction. As x goes toward negative infinity, follow the graph. Y goes toward negative infinity. All right, look, x gets more negative, y gets more negative. X gets more negative, y gets more negative. X gets more negative, y gets more negative. So we could also say this for this graph. Okay, that's what end behavior is. Discontinuity. I've used the word continuous before. I've said polynomial functions, which we studied in chapter 8, are continuous. Therefore, the intermediate value theorem can be used. Because in order to get from a negative y value to a positive y value for a continuous function, it's got to cross the x-axis. Guys, please focus. I hope you're all paying attention. It's got to cross the x-axis, and it's a continuous function. So what do you think a discontinuity is? What do you think a discontinuity really means? What's a discontinuity? Not if it doesn't cross the x-axis. Good idea, though. I like the concept.
There's like a gap in the line.
If there's a gap somewhere, maybe the function is broken into pieces, or maybe there's something that makes the denominator 0. Right? Something that makes the denominator 0 makes the fraction undefined. Well, if it's not defined, you can't have a graph of it. So a discontinuity would be something like this. There's a hole in the graph. Or a function that looks like this. And we're going to see this shape in a moment. These are rational functions. And for some reason, the graph cannot get to this location. The graph gets closer and closer to that location, but to continue the graph, it's going to go down, you pick your pen up, and you continue on the other side. Anytime you have to pick your pen up to follow along a curve, it's a discontinuity. That's the easy way to remember. If you were to follow that curve, you have to pick your pen up to either go over a hole or to go over, which we're going to call soon a vertical asymptote. It's called a discontinuity. So we're going to see it for discontinuities. In the fourth term, we call an asymptote is any line that a function approaches indefinitely but never gets to. A simple example. I don't know. How far do you think I am from that academy? Give me an estimation. I don't care. 10 feet. 10 feet? Reasonable. Let me give you this fact point. If I take a big step, that's 3 feet. How many big steps do you think it's going to take me to get there? 4 or 5 big steps, so maybe I'm like 15, 20 feet or something. So if I cut my distance in half, I'm about right here, right? So now I'm about 8 feet. Cut that in half. Where am I at now? 4 feet. Cut that in half. About 2 feet. Cut that in half. On 1 foot. Cut that in half. And half a foot. Never gonna get there?
No.
Why not? Yeah, you learn that if you keep having stuff over and over again, you'll never get to 0. What's that called again in science? What's that example of in science? It's a very obvious example. You're not in chemistry yet, but you probably should have heard of this. Maybe in middle school. Radioactive elements have what? Half-life. Who said that? Half-life. Their radiation dies off, half of it, over a given time period. So theoretically, will a radioactive substance ever become neutral? Because it keeps halving, right? Halving. Half the mass is radioactive after 10 years. Another 10 years go by, half the mass is radioactive. So do you see how we're never going to get there? You understand what I'm getting at so far? Okay, that's what an asymptote is. The example, one second. The example at the top right, let's go back up to this example up here. See the blue graph on the top right? This graph is getting closer and closer and closer to y equals -3. But it's never going to reach that. It gets closer and closer and closer, but it just keeps getting closer. It's asymptotic because it gets closer to what's called the asymptote, a line such that the distance between the curve itself and the line approaches 0 as it tends to infinity. So the distance, the gap between this, ready? Watch. Here's the graph. Closer, closer, closer. It just keeps getting closer, but it never gets to be on the line itself. Even though if you look on a calculator, it'll look like it's pretty much there, because the pixels are not small enough to do it. But it'll never get there. That's what an asymptote is. Okay, that's what an asymptote is. Inigo, you had your hand up.
I mean, but in math, isn't it there like in this theory that if you get to a number small enough, then it might
Sure.
be there?
At a certain point in time, what you would say is that the difference between the curve and the actual asymptote is so insignificant because it's such a small percent of where it was that you might as well say that it's at that location. But theoretically, you never get there. That's what I'm trying to get at. A lot of math that I personally didn't study, I studied engineering, it's all applications. You learn about how to apply math. So whenever I try to teach you guys stuff, I always harp on word problems because they're applications, they're real life stuff. A lot of math in college level math, if you're doing actual math as a major, is very theoretical. Very. And this is a concept that's highly theoretical, but realistically, yes. You eventually will get to that location because you're getting so close to where it was. Okay? So yeah, you have to use common sense along the way. All right, and a lot of the time, by the way, in engineering and physics, you make what are called assumptions. For example, you might look at a projectile's motion in the air and assume that air resistance is negligible. Why? Because maybe it really doesn't affect the projectile's motion that much. Turns out it does. But the math involved in it is very difficult and involves calculus, so you don't really use air resistance with math problems in physics until you get to AP Physics. When you take AP Physics as a senior, when you're studying calculus also, you learn about air resistance because of that. But prior to that, you consider it negligible because it doesn't have that much of an effect to the point where it really is necessary if you can't actually utilize it. Okay? So you make assumptions along the way. That could be an assumption you make. All right. Let's begin with the first section. We're calling this E-1. So, the first 3 things we're going to look at here are domain restrictions, vertical asymptotes, and holes, which are all really the same thing. Okay? And take a look at these first 3 graphs here. These are graphs that are demonstrating what we call rational functions. Rational functions traditionally have bounded shapes. What does bounded mean? If I'm bounded, what does that mean physically if I was bounded?
Restricted.
Restricted to some limitation. Maybe I'm inside of like a, I don't know, you ever see like those magicians that have to escape this little like box and it's filling up with water and they're all tied up and stuff. That'd be like bounded. You cannot go beyond a certain limitation or restriction. Look, you can barely see it, but look carefully at the notes. There are blue dashed lines. Do you see them? The blue dashed lines are asymptotes. Those are your bounds. You cannot cross the vertical ones. It turns out, actually, though, that you can cross the horizontal ones, and you saw that earlier. Remember with the car and the speedboat? What would it do? It would do this, ready? So you're constantly crossing over the bound, the point that you're going toward. That's what this is showing you here, horizontally and vertically. Now, where do these limitations vertically and as wholes come from? They come from what are called domain restrictions. And we've done this already. You did this on your test the other day. It was one of your multiple choice problems. I gave you a rational function, which was two quadratics, and said, which of the following values cannot be a value for x because it acts as a domain restriction? Pretty much you're asked, what makes the denominator what? 0. That's really the question you're being asked here. That's it. This whole topic, E-1, is about what makes the denominator 0. We're going to go into a lot more math about that, but that's what it's about. Okay, what makes the denominator 0? So let's scroll down a little bit and take a look at domain and vertical asymptote. So first, we call the independent variable x, which really does not matter. But what we're trying to figure out is what value of the independent variable makes the denominator 0. So this one is obvious. It's right here in front of you. 3x minus 6, just set it equal to 0. You get x equals 2. So as a result, your domain for this function is x cannot equal 2. Or in interval notation, there's your domain. So you have set notation and interval notation. So that means that this graph is defined from negative infinity to 2. It's undefined at 2. And then it's defined again from 2 to infinity. Why do I have parentheses and not brackets? Because I'm not including 2 in the actual domain of the function. Is that clear? So, before we go on to the next slide, take your calculators out, please. And if for some wild reason you don't have it, at least throw the calculator out on your iPad. This is one you can see on your iPad too. Do me a favor and type this function in. What do you have to remember when you type this function in? Please, numerator and denominator need parentheses. You have to do it. If you don't, you will not graph the correct function. When you hit Y1 and type this in, please hit zoom 6. Hit zoom 6 to standardize your graph, please. Load up graphing calculator on your iPad for now. I just want you to see what the graph looks like. So, can you show me real quick, just with your hand, what does it look like? I know it's weird. It's kind of weird. Yeah, I saw a logo like this and like this. You're all doing this, right? Why are you doing it twice? Why are you doing it twice? Why do all of you do this? It has two what? Branches? Pieces? Right? Would you agree with that term? Is that a good term for that? There are two branches to the graph, or two pieces to the graph. Now, where do those pieces act about? What vertical line? What vertical line can you not see that's really actually there? What vertical line do you not see that's kind of separating the two branches, really? There is a vertical line that's separating the two branches. What do you got, Chandler?
It crosses x equal 2.
X equal 2 is the vertical line. Well, look. What was our domain restriction? X could not equal 2, correct? So could this graph ever equal 2? So 2 is your bound. 2 is your limitation. It is your vertical asymptote. I want to graph this to see it. So you guys could all see it real quick. Here's what it looks like. Forget the horizontal asymptote. Don't even worry about that yet. I just want to look at vertical today. I don't care about the y values. That's what the graph looks like. Oh, come on. Is this AirPlay really not working suddenly? Hold on, let me refresh AirPlay. Alright, you see the function now? So we can clearly see that if we put a vertical line on x equals 2, it would separate these two portions of the function. But this is still one function. You only typed it in y1. You didn't put something in y1 and y2. This is an example of a rational function. Put a dashed line at x equals 2. Okay, and there's our label. That is our vertical asymptote. That is our vertical asymptote. So, tell me, James, what's happening from the right as I approach 2?
From the right to left, it's like.
From the right to the left, what's happening as I approach 2?
It's concave up, but it's stopping at 2.
It's concave up, and it's approaching 2. What's happening to the y value, James?
It's gonna keep going up.
It's increasing.
Yeah.
So this function approaches 2 from the right and increases. Where is it going toward? What's all the way up there? All the way up. Infinity. Now, Inigo, from the left, it's still approaching 2, isn't it?
Yeah.
From the left? But where is it going toward now?
Negative.
Negative infinity. So, we talked about end behavior with horizontal parts. This, you're going to see in pre-calculus. In calculus, you're going to call this a limit. You can jot this down if you want to. It's not something that you need. I'm not going to test you on this term. But the limit, as x approaches 2, of this function, f of x, from the right-hand side, it goes to infinity. And what do we say? From the left-hand side, it goes down toward negative infinity. The negative symbol on the other side of the 2 means from the left. This means from the right. Just some notation that I'm not going to test you on this notation, but you might as well be familiar with it. You'll see it, okay? You'll see it in your junior year right away. So from the right-hand side, it goes up toward infinity. From the left-hand side, it goes down further and further and further toward negative infinity. If there was enough time in the year, in an ideal world, you guys could learn pre-calculus and calculus at the age you're at now. You honestly could. It's just that the system that we have set up enables you to have to space things out so much. If you really like math, I mean, imagine if you had 3 periods of math a day. It'd be like the best school day ever. 3 periods of math, you could learn all of algebra, geometry, and recalc in your freshman year, and you would easily be able to keep up. You would, if you had the time set aside for it. But obviously, we want well-rounded students, so you learn more about yourself, which is great. Personally, I think it'd be awesome if you could kind of go on a track. In European countries, you know how it works? When you get to 9th grade, you choose either science and engineering, math really. You choose humanities, social studies, law, English, and then you choose, the third is like languages. Languages, and sometimes religion is in with languages actually. So those are like the 3 sectors you go, which is kind of like what your classes are, think about it. You have 2 math science, you have 2 humanities, and then you have your language and religion. Those are your 6 classes. So, unfortunately, this is something that you're not going to see till junior year, but it's not difficult to understand. That's why I'm showing it to you now. Okay? If you go to the next, exactly what we're talking about. Look at the table of values I have here. You can do this yourself. You can see for yourself. If you make x get closer and closer to 2 from the left-hand side, look. This is at 1. Follow me, please. Look up. At 1, right here, the x value, the y value is negative 0.7. At 1.5, we're already here, down by negative 2, right here. Then at 1.8, I'm already getting closer. 1.9, 1.99, 1.999, I'm getting closer and closer and closer, but it's getting further and further negative. Look at the number. It's getting bigger and bigger in the negative direction because it's going toward negative infinity. But from the right-hand side, I look at this number. This is 3. 3 has the y coordinate of 2. Well, there it is, 3, 2. Then I go to the next, 2.5, comma 3.3. That's right here. So as it gets closer from the right, this number gets larger and larger and larger. Thus, it's approaching infinity when it approaches from the right. This is a numerical representation of what an asymptote is. Okay, those 2 tables there are showing you numerically what an asymptote is. You can do this yourself if you don't believe me. I assume you would believe me, but if you want to check, which you can do right now, do it now. Hit second, and then hit graph, please. it should pull up your XY table like this. Now, if you already have numbers in there, you can just press delete and hopefully they all go away. If they don't, your settings are different than what I'd like them to be. If they don't all go away, press delete and see if they all go away. If they don't all go away, that's okay. Just press second and then hit window. And under your table settings, it says table setup. Under independent, change that to ask. Go over to ask and hit enter. If you didn't follow that, just raise your hand so I can go through it again. Press second, hit window, go down to independent, and go over to ask and hit enter. Now press second and hit graph again. Your table should be empty at this point. If it's not empty, press, okay, good. So now press second and then hit graph. So your table's empty. Your table should be empty. You could type in X values now. So go ahead and type in 3. Then enter. 2.5, enter. 2.2, enter. 2.1, enter. Pretty much type the table on the right here that you see. Okay, 2.1, 2.01, 2.001. It will eventually probably say 2 actually. Oh no, for your calculator. Oh, sorry. It will eventually might give you an error. But this number will get larger and larger and larger. It might even put it in scientific notation eventually if you keep getting closer and closer to 2 from the right-hand side. But I want you to be familiar with entering data into your calculator using the table feature, but you should really have it on X. So you can type in whatever you want X to be, unless you needed X for 1, 2, 3, 4, 5, 6, 7, then you can put it on auto, so it automatically does 1 through 7 using increments with delta values of 1. Okay? So again, please reiterate to yourselves or recognize that really, when we plug in 2, go back to the original function, go to your y equals and look at it. When you plug in 2, what's going to happen? It's undefined. If you type 2 in your table, it's going to say error. It's going to say error in your table because you can't plug in 2. Look, when you do h of 2, you get 4 over 0. It's undefined. 2 was the value that made the denominator 0. Okay? So from our conclusion, or what we can draw from our conclusion here, and our conclusion is the following. We can see that the independent variable is the cause, or thing that causes the denominator to become 0 cannot be included in the domain. Okay? We can say this is a discontinuity. It's either a vertical asymptote, which is what we have, so underline that for this one. Okay, that's what this is. X equals 2 is called a vertical asymptote. There's another type that we're going to look at, which is also called a hole, or which is also a discontinuity called a hole in the graph. A hole. All right, so to see this, let's take a look at the second example here. You can read further on if you want, but go ahead and factor your original, please. That's how you start these problems. So factor the denominator, please, of this new example here. The numerator can be factored as well, please. Factor GCF out of the numerator, and then factor your denominator. So rewrite this in factored form is the easiest way to start all these problems. What do you got in factored form? In factored form. Should be quick, right, guys? This should be real quick. You should be able to factor this. Jeff, go.
X minus 6 times X plus 2.
Yeah. X minus 6, X plus 2. What's the numerator, Inigo? What does that factor into?
Just 2, and then X plus 2.
Convenient. Where's the convenience that I'm talking about, obviously? Well, X plus 2. So, tell me something. If I plug in 6 into this function, what's the value of the function? It's what? Undefined. It's something over 0. Would you agree? If I plug in 6, it would actually become, to be exact, 16 over 0. If I plug in 6, it's 16 over 0. But what if I plug in negative 2? What if I plug in negative 2? But what would it be? What would the actual value be? Plug in negative 2 in the top and the bottom. What do you get? 1 over what? Alex?
0.
0 over 0. We've never talked about that before. You've never heard of this. You've heard of undefined being over 0, a number over 0. 0 over 0, we can underline this, it's already italicized. This is called indeterminate. Indeterminate, it's italicized, but if you want to underline it, you can. Whenever you get 0 over 0 from a function, it's called indeterminate. Indeterminate means unknown, really. It means unknown. And what's interesting is this. It means that at that x value, oh, this should say g of negative 2 here. Damn, it's a typo. I gotta fix that. It should say g of negative 2 equals 0 over 0. Not just negative 2 equals 0 over 0. Please fix that. Microsoft Word drops number in front of parentheses with an editor all the time, that's home. And I don't know why. It's always when we fix this stuff. And it never really knows. So we're going to see here that this becomes 0 over 0. We're going to call this a hole. And we're going to see it on the graph. We might run out of time in a minute with Bell by Ring. It's 10:22, it's a C right. Okay, but what we're going to notice is, take a look at this table here. I'm going to do the same thing. I'm going to take a numerical approach from the left. As I get closer and closer to negative 2, we're going to notice this goes towards it. We'll pick up with this tomorrow. Okay? No homework tonight. We'll be able to finish this tomorrow for sure. So you'll definitely be able to do this homework over the weekend. And we'll probably start the next section tomorrow also. We were talking about holes yesterday in the graph. And we talked about just the simple feature that a hole is caused by getting 0 over 0 when you evaluate a number in the function. So the question is, what is that number? Usually that number is something that makes the function what we call indeterminate. Indeterminate. Now, the question or the idea here is, how do you figure out what the y value is for the hole in the graph? So let's take a look at a simple graph. Graph yourself an xy axis. Just simply draw a linear function. Doesn't matter what it is. Put a hole in the middle of the function somewhere. So the x-coordinate here, this value, comes from whatever makes the rational function indeterminate. So in the example we just looked at, right? In the example we just looked at up here, we saw that at negative 2, this became indeterminate. Right? Negative 2, yeah. Now, in this one, we'd say, well, the x value is whatever caused the denominator to become 0 and the numerator to become 0. So if I was writing this function, what would I know has to be in the numerator and the denominator? What factor must be in the numerator? Let's call this, let's say it's 3 for now. What has to be in the numerator and the denominator? Remember, where there's a hole, the function's value is indeterminate, 0 over 0. What would make this 0 over 0? X minus 3 over x minus 3. Again, plug in a 3. What do you get? 0 over 0. And look, there's a hole at 3. This 3 on the graph is corresponding to the fact that you can't put a 3 in this fraction because it makes it 0 over 0. So a hole is caused by a factor that repeats in the numerator and the denominator. Now, with a rational function, this cannot be the only thing in the numerator and denominator, so the numerator must also have something else. We'll call that x minus 1. How do I know it's x minus 1, or why am I choosing x minus 1? Can we figure that out? What's the y-intercept of the graph? Ish. What's it around? It's around negative 1. So wouldn't the graph y equals x minus 1 be a linear function with a y-intercept of negative 1 with a slope of 1? So I know we don't know what this point is yet, but the concept here is that if I think about this as a linear function, simply reduce these two, and we see what the actual function really was. You see that? So the repeated factor in the numerator and denominator has no effect on the graph beside creating a hole in the graph at the location that would make the fraction 0 over 0. This does not affect the graph. Cross this off. And that's the function you have, x minus 1. Now, if that's x minus 1, what should the y-coordinate be right there? Plug in a 3. What should the y-coordinate be? Again, reduce these. Plug in a 3. 3 minus 1, 2. This y value here is 2. So to find the y value for the hole, for its location, which you're going to have to mark on the graph, a point of discontinuity, to find that y value, you simply think about reducing the rational function like that. And then evaluating the reduced rational function at the location. Right? This 3 goes in right here for that x. Evaluating the reduced rational function at the location where the hole would be. The y value is 2. 3, 2. Is that clear? Does that make sense? The idea? It's a different kind of discontinuity. It's not the same as a vertical asymptote. A vertical asymptote, the graph becomes unbounded. It goes off to infinity, and the other side of the graph drops to negative infinity. Or they both go up to infinity, and they ride along an asymptote. Here, a hole is completely different. All it is the same function you would have as a reduced function, which in this case, the reduced function is r of x equals x minus 1, and you reduce x minus 3. So this reduced function is what you're seeing here. All right, let's take a look at the next example for this. Let's look at example 3. We'll jump down to that. Determine the value of x that causes f of x to be undefined. Classify each of these discontinuities as either a vertical asymptote or a hole. Now remember, if it's a hole, we actually call it indeterminate. So you're looking for both of these in this case. The general term undefined, though, it's all-encompassing for both, really. So we take a look at this, and right away, what do we think to do? What do you think to do? They have to do for all these problems to make the first step. Factor everything. So go ahead and factor numerator and denominator. The denominator, obviously, you have to factor out a GCF first. Take out that x in the denominator. See the resulting quadratic. And then be careful. I made the common mistake of putting x plus 2 right away, because x plus 2 was in the numerator. So I thought in my mind, it might show up in the denominator. So I started by putting x plus 2, and then I realized it has to be plus 5, obviously. So just be careful that you don't make that. That's like a careless mistake that you pick up on. But I checked my work. As I go through it, I check it every time. So as I was putting x plus 2, I started writing x minus 5, and I'm like, no, it's got to be the other way around. So always check your work as you're doing it. So what do we see that repeats as a factor in both the numerator and denominator? What repeats itself? What factor is in both? And what does that mean? Nico, what factor is in both, and what does it mean? X? Yeah, so 0 is what would...
0 divided by 0.
That's exactly right. So if you plug in a 0 for x, you would get 0 over 0, which is indeterminate. So right away we know x cannot equal 0. And at 0, comma something, we're going to have what? A hole. When the factor repeats itself in the numerator and denominator, causing 0 over 0 for an indeterminate function, we know that there's going to be a hole. So, how do we find the y value again? From the last example. Do you remember, Alex, how to find the y value for the hole? I know the x value is 0, right? Yeah, so plug in the 0 in, but where do I plug it into? Okay, And I have to make sure that I have the reduced function. So don't plug it in here and here, obviously, or else it's going to make it indeterminate. So get rid of these x's, plug in a 0 here, here, and here. See what you get. Plug in a 0 at the top first, you're going to get 6 on the top. Plug in a 0 at the bottom, you're going to get negative 10 on the bottom. So we're going to get 6 over negative 10, or negative 0.6. So here is the y value of the whole. Negative, again, 6 over 10. So always, to get the y value of the whole, use the simplified rational function. And that simplified function there is no longer indeterminate at that point because you've gotten rid of those factors. After that, what else do we know? What else do we know when we're looking for discontinuities? Morgan, what else do we know? Where are the other discontinuities?
In the slope. Maybe the slope.
What do you mean?
Like, on the earlier example, you got when you plugged in the y values.
Well, my question though is like, where are the other vertical asymptotes, the discontinuities? What's the domain restrictions? What's messing up my denominator? We had 0 as one of our options, right? That came from right here, right? So what are the other two values of x that cause... Good. So we know this, it can't be 2, and it can't be negative 5. Those are my other domain restrictions. Well, at those locations, what do you see? Look at the graph. I mean, if it's not clear, look at the graph right here. You see vertical asymptotes at negative 5 and at 2. Again, domain restrictions that cause the function to be undefined are vertical asymptotes. Domain restrictions that cause the function to be indeterminate are holes. Two different types of domain restrictions. Okay? Now, go to your calculator, please. You got to practice this. I know it's annoying, but you got to practice it. Type in the original function, please. Do not factor it. Put the original function in. Parentheses around the numerator, parentheses around the denominator. Once you've hit graph, go to your table, please. Once you've hit graph, go to your table. And when you do that, what I want you to do is this. I want you to approach the number 2. Approach it from the left. Approach the number 2 from the left. So big values you should plug in for x so that you're getting closer and closer and closer to 2. So we can see that this is going to negative infinity. So we can prove it to ourselves. So pick like 1.5, 1.9, 1.99, 1.999. Get closer and closer to 2 from the left-hand side. What's your highest value in the negative range for the y value? What did you get for the highest one? You're plugging like 1.999. What'd you get? Well,
Negative 17,000.
yeah. All right, negative 17,000. Is it obvious? Is it evident to see that? As you approach 2 from the left, the function goes unboundedly toward negative infinity. How about from the right? James, what numbers would you choose from the right to approach 2? When you type it in your table, what numbers are you going to pick for x? What would this be for x?
2.1.
Okay, 2.1. What after that?
2.8.
2.01, and then
2.141.
yeah, just literally keep adding zeros every time. That's all you're going to do to get closer and closer to that value. And in that example, you should see the number getting larger and larger and larger in the positive direction. You don't have to do it for -6 or -5, but it's the same thing, right? Okay, for -5, it's the same behavior. From the left, it's going toward negative infinity. From the right, it's going toward positive infinity. How do I write that? Let's write that together so we can see that notation. Let's write this. So we'll say, this pre-calculus and calculus notation. The limit as x goes to 2 from the right of, this is defined as f of x. So the limit as x goes to 2 from the right, which means, again, you're going to 2. We're starting on the right. We follow the graph. It's going up to infinity. The limit as x approaches 2 from the left looks like this. And it's going down to negative infinity. And I'm not going to write it for -5, but it's the exact same thing. Where you have a 2, you have -5 plus, meaning -5 from the right, and then -5 minus, meaning -5 from the left. That's what the behavior is. I'm having you do this honestly, because in a moment, we're going to do this with horizontal asymptotes, so just to get the practice down for the notation. Okay, so do you understand limit? Limit is simply saying this. Where is the function headed? Where is it headed physically? Well, as it's going to 2 from the right, it's headed up. As it's going to 2 from the left, it's headed down. It's giving you directionals, that's all it is. If it's headed toward a specific value, then that value will sometimes be written. Maybe it's headed towards 7. In this graph, it would literally say 7. For example, what is this? Tell me this, please. What is the limit? Let's see who understands what I'm saying. What is the limit as x approaches -2 from the right? What is the limit as x approaches -2 from the right? It's not a trick question. Jeff? 0. How about from the left, Jeff? 0. Jeff is saying, well, it's common sense. Take a look. Here's -2, right? Approach it from the right. It's going toward, oh, look at that. That's 0. The y value is 0. This y value would be 2. This y value would be 4. Well, from the left, it's also approaching 0. So the limit from the right and the left are both 0. So in calculus, what you're going to do is you're going to say, well, okay, if the limit from the right and the left match up, then the limit exists there. This is really lame, but, and I know a lot of you have seen it, so don't lie. How many of you have seen the movie Mean Girls? Honestly, raise your hand if you have. Nobody? It's something, I've seen it myself. Whatever. In the movie, there's a part of the movie where they say like the limit exists or the limit does not exist. This is what they're talking about. If the limit from the left and the limit from the right don't match up, the limit does not exist. That's that line in the movie. Here you could say that the limit as x approaches -2 in general goes to 0. And this statement can be made because the right and the left approach, right, these both approach 0, which means the limit in general approaches 0. All this says is that the function is continuous. If this is true, the function is continuous, which is what we have there. Okay? The value of the function would also, I should say this, the value at -2 also has to equal 0 for it to be continuous, which is true in this case. All right, let's take a look at the second section. Let's look at E2. For this, by the way, your homework is on the next here. I want you to find all holes and vertical asymptotes, and then graph them on your calculator and actually sketch the graph. Sketch in the vertical asymptotes with dashed lines, find the location of the hole, the y value of the hole, put an open hole or an open circle on the graph. So do exactly what we've been doing with E1.